this video we learn how to calculate the pH for a weak acid solution. Right, we're going to make a solution with ammonium chloride, which is a salt, and the concentration is going to be 0.20 molar. Right, so we put this in water, and this is a soluble ionic compound which dissociates into the constituent ions. Right, so you're going to have ammonium ions on one side and also chloride ions. The purpose of this problem is to calculate the pH of a solution. So what that means is that those ions should have some acid-base properties. Of the two ions, the one that has more significant acid-base properties will be ammonium, and the ammonium ion happens to be a weak acid. Okay, so if it's a weak acid, what that means is that when you put it in a solution, it will generate protons, and it does. So the equilibrium will be like this: H plus, aqueous, and then ammonia in aqueous solution. So it turns out that the equilibrium constant for that dissociation, that acid dissociation, is known. This case of A happens to be equal to 5.6 10 to the minus 10. Then the question will be, please calculate what the pH of the solution is. To calculate the pH of the solution, we need to know what the concentration of protons is at equilibrium. And because this is an equilibrium that has a quite low equilibrium constant, what we must do here is utilize an ice diagram to calculate the concentrations at equilibrium of all of the species involved. Okay, so let's write here the ice diagram and see what that pH is. Okay, notice that because this fully dissociates, the concentration of ammonium ions will be 0.20 molar as well, and initially you will not have any protons or ammonia. Right, so when we draw here the rows of the ice diagram, initially we have 0.20 molar of ammonium, then nothing of protons and nothing of ammonia. The change will be minus X for ammonium. This dissociates a little bit, and then we have plus X and plus X for protons and ammonia, because the stoichiometric coefficients are all 1, 1, 1. Right, so at equilibrium we will have here 20 minus X, X and X, and then we can take these values at equilibrium and plug them into the acid dissociation constant and then solve for X. Alright, so we have that this is going to be equal to the concentration of protons, concentration of ammonia, over the concentration of ammonium ions. Alright, and then what we have here is that when we look at the, these are equilibrium concentrations, so we look at the equilibrium entry in our ice diagram, and that is going to be equal to X squared over 0.20 minus X. Alright, so that is the equation that we have to solve, and in principle this will be a quadratic equation, but it turns out that we can use an approximation that is going to work very well. Notice that the equilibrium constant is very, very small. What that means is that the equilibrium will be very little displaced to the right, and ultimately what that means is that this X will be extremely small. Alright, so what we do then is incorporate here the approximation that you can neglect X with respect to 0.20, and then that makes that equation much easier to solve because you don't have to use the quadratic formula. Alright, so solving for X, we find that this X is equal to 1.1 10 to the minus 5. Okay, so the next thing that we do is compare this solution to the number that we're neglecting it against, and the ratio of those two numbers is well below 0.05, so the approximation is quite valid in this case. Okay, so that is the concentration, the X that we have here, which also happens to be the concentration of protons at equilibrium. Right, so we have that will be the concentration of protons at equilibrium from our ice diagram. Right, so we're just one step away from being able to calculate the pH. Notice that the definition of the pH is the minus base 10 logarithm of the concentration of protons. So then the only thing that we need to do is just simply plug this concentration of protons at equilibrium in our pH expression and then solve for it. And that pH happens to be 4.96. Okay, so this is how you calculate the pH of a weak acid solution. What you have to do is write an ice diagram and then solve for the concentrations of proton at equilibrium. Right, moving a little bit beyond the calculation of pH, another thing that we can do in this type of problems is calculate the percent of dissociation of the acid at equilibrium, right? So there is a very straightforward way to calculate that, and that is utilizing this formula. We can always define the percent dissociation of the acid, percent dis, simply as the amount of acid that has dissociated over the amount of acid that you had initially. Okay, so to write this in a generic form, the concentration of acid that you had initially is going to be HA sub 0. That is what means initial concentration of the acid. And then the amount that has dissociated will be identical to the amount of protons that you have right here, as long as this acid only has one proton, right? Because any molecule of the acid that dissociates is going to appear as one proton in this case, right? So in essence, what you're doing is simply calculating the concentration of protons at equilibrium, dividing that over the initial concentration that you had, and then you multiply these by 100%, and that will be the percent dissociation of that weak acid. Okay, so we can do this for the current problem, because we have all of the data. Right? The concentration at equilibrium happens to be 1.1 10 to the minus 5 molar. The initial concentration of my weak acid is 0.20 molar, right? I multiply this by 100%, and this happens to be a very small number, 5.5, 10 to the minus 3%. Okay, which means that only a very small fraction of the initial acid dissociates. Okay, ultimately what that means is that the pH is not very low, right? So this is not a strongly acidic solution. It's quite close to neutral pH, and all of this is governed by the really small value of the equilibrium constant. All right, so in this video we have learned to do a couple of things. First, we have learned how to calculate the pH for a weak acid solution, and then we have used the results to calculate the percent dissociation of the weak acid.